In this lecture, I want to define the Riemann tensor. The Riemann tensor is a very important tensor in general relativity because it accounts for curvature. So how do we measure curvature in space-time? In general, there are two ways to measure curvature. One way is intrinsic and another way is extrinsic. An extrinsic way to measure curvature, for example, is if you are outside of the space that you want to measure, let's say. So let's say that you have a sphere. This sphere is embedded in some space and you can measure its curvature by observing the sphere. So this is an extrinsic measurement if you want. So it's not very precise, but you can get the idea. Whereas if you want to measure the curvature of space-time, you don't have a way to measure its curvature extrinsically. The only way that you can measure its curvature is intrinsically, which means that you are embedded into this kind of space and you have to find a way to measure its curvature. So conceptually, this is more difficult, but it is not so complicated. One way to do it is if you, for example, consider a small loop. Let's consider a small loop. It's some kind of rectangle, let's say. So I will draw a rectangle here. You have to think of this as an infinitesimal rectangle, and we start at one of the vertices of this rectangle, and we move, let's say, anti-clockwise, like this, and then we get back to this point, to this initial point. Let's say that we want to parallel transport a vector. So we start here at this point with some vector that it is a 4-vector v gamma, let's say, and we transport it along this curve, this rectangle here, this infinitesimal loop. If there is no curvature, when we get back to this point, this vector here will not have turned around, so it will not have changed, it will remain the same. Whereas if we see curvature, then maybe this angle, there is some angle here, let's say delta alpha, which rotates, which creates an infinitesimal rotation of this vector v gamma. And this is how you can intrinsically measure curvature. So what we want to do is we want to find the change in the vector v gamma, and we can call that change delta v gamma when we go around this loop once. So this rectangle is infinitesimal, let's say, so the distance between these 2 points here is dx mu. Here we have dx nu, where nu and mu are of course indices which can vary from 0 to 3. So you have to think of this rectangle as one possibility, but you have plenty other possibilities, because nu and mu can have different values. And let's also give a name to these vertices. We have A, B, C, D. And let's say that this point here is the point x mu, x nu. So we start at this point, and then we move infinitesimally to the right, then we move above, and then we go around this loop like this. So how can we find the change delta v gamma around this loop? Well, this change will be given by some contributions. The contributions are given by the change of the vector v gamma along AB, so the change along this first part of the loop. And then we have some change delta v gamma BC. Then we have some change of v gamma along CD, and also we have some change of v gamma along DA. Now these changes also have a sign, because for example here along CD we are moving from the right to the left, so therefore this delta v CD can also be thought of as minus the change of v from D to C, of course. And something similar for this one. This can also be thought of as minus the change of V from A to D gamma. We can rewrite this total change here like this. We have delta V BC gamma minus delta V gamma AD minus delta V DC gamma minus delta V AB gamma, just like this. Why did I rewrite it like this? Well, because in this case we can easily see how we can rewrite these differences here. Because take a look at this one. Here we first change V along AD and BC, and in that case we are varying the coordinate x nu, and after that we consider the difference between them. So in this case we are changing the coordinate x mu. So first we change x nu and then we change x mu. So it's as if we are considering first the covariant derivative along nu of v gamma times the change delta x nu. So this is like some kind of change of the vector gamma v gamma along the coordinate x nu. But then we also have to consider the change along mu. So we also have to consider the covariant derivative with respect to mu, and then we also have delta x mu, of course. Something similar for this one, but if you take a look at it, this is different from this one here. Because first we change, for example, when we consider the change of v along dc, we are changing mu first. And also in the case of VAB, we are changing mu. So first we have the covariant derivative along mu of V gamma times the change delta x mu, and then we have to consider the change along nu. So delta nu, and then we have delta x nu here. So you can see that the expression that we get is a tensor because we have covariant derivatives. So the total change delta V gamma will also be a tensor. So we will rewrite this. Now we have to do some calculations because we also want to express the covariant derivatives according to the formulas that we have, the formulas of covariant derivatives of contravariant vectors. Because in this case you can see that, for example, delta mu acts on something that contains the index gamma, because nu and nu are summed over, so they do not play a role for this tensor here. And also this covariant derivative acts on V gamma, and therefore we have the covariant derivative of a contravariant vector. So I'm going to rewrite it like this. We have delta mu, I will rewrite it as is, and then we have the covariant derivative of V gamma, and I can rewrite it as the Euclidean derivative del nu, delta, let's say the partial derivative with respect to nu of V gamma plus Christoffel symbol gamma nu alpha V alpha. Then we have delta x nu, delta x mu minus del nu. Here we have del mu V gamma plus Christoffel symbol gamma mu alpha V alpha delta x mu delta x nu. And now we can also use the definition of this covariant derivative here and also this one. So we'll replace their expressions. We have partial with respect to mu of del nu V gamma plus Christoffel gamma nu alpha V alpha. And then we have plus Christoffel symbol gamma beta mu del nu V beta. So I'm calling beta this index here. We have to sum over beta, of course, and gamma will appear here in the Christoffel symbol. And we have plus gamma, beta, nu alpha, v alpha. And then we have to consider this part here. I will also factor out these differentials here, so I will not write them here. So let me put a bracket, and I have to remember that at the end of my expression, I will have to multiply by these two differentials here because they appear in both terms and they can be factored out. So here I will have plus, and I will go below here, and of course I have a minus del nu, so I have partial nu, and then I have del mu v gamma plus Christoffel gamma mu alpha v alpha, and then I have minus Christoffel gamma beta nu, and then I have del mu v beta plus gamma beta mu alpha v alpha, and then I have to multiply by delta x mu delta x nu. And now I just have to do some very simple operations. I have to consider the expansion of these terms contained inside these brackets. So I have to calculate these derivatives here and multiply these terms, calculate this derivative, and also multiply these terms. So I have to expand that expression. So I will have del squared mu nu v gamma plus del mu gamma lowercase gamma nu alpha v alpha plus gamma lowercase gamma v alpha del mu v alpha plus Christoffel gamma mu beta del mu v beta plus gamma lowercase gamma mu beta gamma beta nu alpha v alpha plus, and now I will go below, I have minus del squared nu mu v gamma minus del nu gamma lowercase gamma mu alpha v alpha minus gamma mu alpha del partial nu v alpha minus Christoffel gamma nu beta del mu v beta minus Christoffel gamma nu beta Christoffel beta mu alpha like this times v alpha. And then I have to multiply by delta x mu delta x nu here. And now it seems complicated, but actually some terms will cancel, because here, for example, we have the second derivative of v gamma with respect to mu and nu, which cancels this term here because the order of differentiation does not matter in the case of Euclidean derivatives, right? Then we also have this term here, which will cancel if you take a look this one, because beta and alpha are dummy indices, and if you take a look at these expressions, they are the same with the different signs, so they will cancel out. And then we have this one, which will cancel this one for the same reason. Beta and alpha are dummy indices. So this expression will simplify quite a lot. So the total change v gamma can be written like this. It's it's partial mu Christoffel gamma mu alpha minus del mu Christoffel gamma mu alpha plus Christoffel gamma mu beta Christoffel beta mu alpha minus Christoffel gamma mu beta Christoffel beta mu alpha. And then here I multiply by v alpha because you can factor it out of those terms. Then you have delta x mu delta x nu here. Now we know that this expression must be a tensor. This delta nu gamma must be a tensor, and then here on the right we have tensors, because this is a tensor, this is a tensor, this is a tensor, and therefore this guy here should be a tensor. And this is the Riemann tensor. So as you can see, this is quite a complicated object because it depends on 4 indices. So we have, I will define it like this. It's R, which stands for Riemann, and this letter will also be used for Ricci, the Ricci tensor, but we will see that. I mean, the Ricci tensor will depend on just 2 indices, so there will be no possibility of getting confused. So we have one upper index that is gamma, and I will call it, of course, gamma. I will put it here. And then we have 3 lower indices, and I will put them here. So we'll have one index is alpha, then I have nu, and then I have mu. So this is one possible way to define this tensor. Of course, sometimes in some books you can find that some of these indices are not in this order. They are changed, but we will use this definition. So this is a definition for the Riemann tensor. We know it's a tensor and it depends on 4 indices, and we will define it like that. As you can see, it's quite a complicated expression. And if you go and take a look at the expression for gamma, and if you recall it, gamma contains derivatives, partial derivatives of the metric tensor and also the inverse metric tensor. And so you can easily understand that this tensor here is quite complicated to calculate. I mean, not complicated in the sense that it is difficult, but complicated in the sense that it is quite an involved calculation, because it deals with lots of terms. Okay, but in principle, this is how you do it, and it can be done. So the calculation can fill up pages, but it is simple. Conceptually, it is quite simple. It is quite, let's say, involved, but it is conceptually simple. Now, let's consider also the expression for this Riemann tensor in a local frame. What happens in a local frame? In a local frame, we know that the Christoffel symbols are just equal to 0, because in a local frame, our metric is Lorentzian. So we have a matrix. The metric tensor will be something like this. I will represent it using this matrix 1 minus 1 minus 1 minus 1, just like this. Okay, and in this case, the Riemann tensor can simplify a little bit, because you can see that these products will cancel. So I mean, they will be equal to 0. So we have R gamma alpha nu mu equal to del mu gamma nu alpha minus del nu gamma mu alpha gamma, like this. And in general, you cannot say that these derivatives here are equal to 0, because we can say in general that locally the Christoffel symbol goes to 0, but its derivatives are not necessarily equal to 0. And finally, if we consider, instead of an infinitesimal loop, a finite curve along which we want to calculate the change of a vector delta v gamma, well, in this case, it is quite intuitive that we have to integrate over the curve that I call sigma, and I simply have to rewrite the expression that I derived earlier. So I have Ricci tensor gamma alpha nu mu v alpha, and then here we have delta x nu delta x mu. You can take a look at these two differentials here that are multiplied together. This is an element of a surface that we can call delta s nu mu, for example. This surface is such that its boundary is exactly sigma. So sigma is the boundary of the surface S nu mu, if you want. And here we have the element of the surface. We have to sum over all these indices nu, mu, alpha. In particular, we should take a look at the indices nu and mu here. If you take a look at this expression, but you can also take a look at the more general one, which is this one, you can see that if you swap the two indices nu and mu, you will get a minus sign. So the Riemann tensor will be exactly equal to minus the same Riemann tensor gamma, alpha, and you swap mu and nu here. So if mu and nu are equal, of course, the Riemann tensor is equal to 0. Okay, so you can also consider the fact that you can sum over nu and mu, where mu and nu are equal to each other, but then of course you're going to get 0. And in particular, this expression, if you expand it, you would have terms like this. So I will not write it completely, but I'm just rewriting some terms here by considering some values that nu and mu can take. So we have r gamma alpha, for example, 0, 1, v alpha del s 0, 1, or maybe I can simply rewrite delta x 0 times delta x 1. Okay, and then you have plus r gamma alpha. You can have 2, 1, v alpha delta x2 delta x1, and so on and so forth. But we have to be careful because, for example, we cannot have r gamma alpha 1, 0, v alpha delta x 0, delta x1 delta x0. We cannot have a term like this without reinterpreting these two here, because if delta x0 times delta x1 is equal to delta x1 times delta x0, because in general it is exactly the case. So I mean they are equal. This product here is equal to this product here. The problem is that this tensor written like this with 1 and 0 like this is equal to minus this guy right here. So you can easily understand that these two terms will cancel if you consider something like this. And this term, for example, would be cancelled by r gamma alpha 1, 2. And then you have something similar here. So you have to sum in such a way that you don't get the result equal to 0. So you have to consider a sum in which, for example, 0, 1 is not cancelled by 1, 0. So either you sum in such a way that this term does not appear, or you can simply reformulate, or maybe you can change, you can reinterpret this product here. So if, for example, you consider, instead of writing this product like this and like this, you rewrite the element of the surface ds nu mu. And in this case it is 0, 1. And you reinterpret it in such a way that delta s 1, 0, which is exactly this, is equal to minus delta s 0, 1. So if you reinterpret delta s like this, and you sum over nu and mu, in this formula a term 1/2 would appear, because you are going to get twice the result. So it is just a matter of convenience, or you can also simply reinterpret this formula in such a way that you are summing terms like this. So you are summing r gamma alpha 0, 1 multiplied by v alpha delta x0 delta x1, then you have r gamma alpha 0, 2, v alpha delta x0 delta x2, then you have plus r gamma alpha 0, 3, v alpha delta x0 delta x3 plus r gamma alpha. Then you can have 1, but it should be followed by not 0, because otherwise it would cancel this term. You can have r1, 1, but this term here is equal to 0 if nu is equal to mu. So you can also start from 2. So you have r gamma alpha 1, 2, v alpha delta x1 delta x2 plus here you have plus, and then you have R gamma alpha 1 3 V alpha delta x1 delta x3 plus R gamma alpha 2, but you cannot start from 0 because otherwise you would cancel this term. You cannot start from 1 because otherwise you would cancel this term. If you put 2, you will get 0, so you will have, the only possibility here is to put 3. V alpha delta x2 delta x3, and then this is it. You don't have other terms actually, because if you consider R gamma alpha 3, and then here if you put 0, you would cancel this one. If you put 1, you would cancel another term, and so on and so forth. So actually, when you sum over mu and nu, you have these possibilities here that are not many, okay? They are just six of them. So you can rewrite the expression like this, or you can just sum over nu and mu, but you reinterpret the sign of the surface, because if you reinterpret the sign of the surface, in this case, the order of these differentials is not meaningless. I mean, you will get another minus sign from here and another and the minus sign from here, so the two minus sign would compensate each other, and therefore you're going to get twice this result here. Okay, so this is just one way to think about it. But yeah, I mean, the most important thing here is that we derived the Riemann tensor, and this will be very important in our theory.